Welcome back to Rock the JVM, folks. I'm Daniel, and in this video, we are going to continue the mini-series on type-level programming in Scala 3. This is the second part of the series where we are going to sort types at compile time. In the previous video, we ordered natural numbers as types at compile time, relying on the compiler's ability to synthesize given values, and we're going to use the same technique and bring it to level 9000 here in this video. So this assumes that you're really comfortable with Scala and with the given feature in Scala 3. And to get started with the first part of the series, I'm going to link the video in the description. As always, I'll recommend that you write code with me in this video, and whenever you need to refresh your memory, just refer back to this video or to the written form at the blog with the link in the description. So I'm going to give you everything that you need in the description of this video. Now, without further ado, I'm going to come back to the code that we ended up with in the previous video where we ordered numbers as types at compile time. Now, to that end, we used the piano representation of natural numbers by this trait that I called nat and the class that I called _0 for the quote-unquote number 0, and the succession between two consecutive numbers by this successor type. So with these three types, we can therefore cover the entire natural set, and to obtain a natural number, for example 2021, you can have successor of successor of successor of as many times as needed to obtain your desired number. Now, to help a little bit with our typing, I created these type aliases _1 through 5 just to type a little bit less while we are doing our tests. Now, in the previous video, we defined a type that I called less than, which denotes a less than relationship between two types A and B, which are both naturals. And we can prove the relationship, for example, 1 is less than 3, by making the compiler generate a given instance of less than between _1 and _3 in this example. And to do that, we followed the mathematical axioms of the less than relationship in real life and translated to given definitions in Scala. So we defined a given instance or a given generator, a given synthesizer for the basic axiom of less than, and an inductive given generator for the inductive step of the axiom of less than. For more details, you can check out the previous video. I explain all of these in great detail. So we have a less than relationship, and as well we have a less than or equal relationship that we can prove at compile time by making the compiler synthesize an appropriate given instance. Now, in this video, we are going to apply a quicksort algorithm for a list of these so-called numbers at compile time. So to that end, we need to define a list type. And in the style of the shapelist library for Scala, I'm going to define a trait that I'm going to call hlist, a higher level list or an heterogeneous list. This is why it's called an hlist in shapelist. Now, this hlist can be in two cases. So I'm going to define a class. So I'm not going to define values. We are operating at a type level, of course. So I'm going to call this hnil, which denotes the empty list, and I'm going to say that this extends hlist. So it's as I've defined a value at the type level. By defining a class, I've defined a new type. And this type is an extension to hlist. And I'm going to define a class that I'm going to call colon, which is the non-empty list. And instead of taking two values as normal value arguments, I'm going to take two type arguments. I'm going to call this a head for h. So I'm going to have an h, which is a natural. So this will be a number, and a tail, which is an hlist. And this extends hlist. So this will be a cons type. This will be a non-empty list at the type level, of course. Now, we are going to make the compiler sort such lists automatically at compile time. Now, if you're wondering how can that be possible at all, or reorder types, I'm going to show you step by step. So I would like you to follow me here in the code, and what we're going to end up with at the end is going to be pretty magical. So on regular quicksort, what do we need to sort a list? First of all, we need to take the head of the list and consider that to be a pivot. The pivot is a special element in the quicksort algorithm, which serves for a partitioning of the list in two halves. A half of the items which are smaller than or equal to the pivot, and 1/2 of elements which are greater than the pivot. So we are going to partition the list into elements less than or equal to pivot and the elements greater than pivot. So we're going to split the list into two. Obviously, we're going to have to traverse the list and separate the elements smaller and larger than the pivot. Then we will need to sort the partitions recursively. And then we will need to combine or concatenate the sorted partitions. So let me give an example of how a quicksort algorithm would work on a regular list. I'm pretty sure you know this already, but let's assume we are going to do a demonstration from scratch. Let's say we have the list 2, 3, 1, 4, and we want to sort that from scratch. The head of the list is 2, and so the separation is going to be, or the partitioning. So I will need to store all the elements smaller than the pivot, smaller than or equal to the pivot without the pivot, so we have just the list 1, and then we have the list 3 and 4. So notice that I've cut the pivot out. Now we need to separate or to sort these partitions individually, so we need to sort 1. Of course, this is the list 1. Then we have sort with 3, 4. Assuming that the sort works correctly, this will yield the list 3, 4, of course. And then we will combine the sorted partitions. So I'm going to have the list 1 plus the element 2 plus the list 3, 4. So this will be the list 1, 2, 3, 4. All right, so we're going to basically make the compiler follow these steps automatically by enforcing some type relationships through the generation of given values. Now, this may sound quite impossible, but I'm going to assure you that this is very possible and pretty magical, honestly. So to do the sorting, we need 3 fundamental operations. First of all, we need to implement a concatenation, quote-unquote, function that is able to prove the concatenation signature of several types. I'm going to show you the format of concatenation. So we need to implement concatenation, we need to implement partitioning, and then we will implement sorting to combine them all. So the operation 1 is going to be the concatenation. So I'm going to define a trait that I'm going to call concat that takes a list, let's call this HA for high-level list A, which is an H list, another list HB, which is again an H list, and I'm going to take a third argument, I'm going to call this O for output, and this is going to be an H list as well. Now, we are going to denote a concatenation instance by saying that the concatenation of HA with HB results in the type O. So this is to say that HA plus HB is equal to the type O. Now, this is not going to be a computation on the part of the compiler, but rather, if we have an instance of concat for HA, HB, and O, that means it's true that the concatenation of HA and HB is the list O. So we're going to make the compiler prove the equality between the concatenation of HA and HB and the list O. So I'm going to define a companion object, I'm going to call this concat, of course, and we are going to embody the axioms of the concatenation operation into given synthesis. So what are the axioms of concatenation? So first of all, concatenating any list with the empty list, so h_nil plus any list is equal to that particular list. So for every L, which is an H list. This is true. So if you concatenate any list to the empty list, you will obtain that same list. All right, this is pretty basic. Now, the inductive step is much more important, and this will allow the compiler to do inference for us. And the inductive step is going to be that if we have HA plus HB equals O, so if we have 3 types for which the concatenation is true, so if the compiler can prove this, then the compiler can also prove, so I'm going to put this a little spaced here so that you can identify the statements. If I have another number prepended to HA, so I can say n colon HA, plus HB, so I'm going to separate this in parentheses. So if I have a bigger list which starts with n, then n prepended to HA concatenated to HB is n prepended to that same output. Think about it. If you have another element here to the first list, you will also have that element in front of the output. So if the compiler can prove this relationship, then the compiler will also prove this relationship. So now we need to encode these as given instance generators. Let's take the basic axiom first. So I'm going to define a given. I'm going to call this basic. And this will take any list L, which is an H list. So for every L in H list, the compiler can automatically generate, on demand of course, a given instance which proves that the concatenation between H0 and L is equal to L. That is to say that the compiler will automatically generate an instance of concat where the first type is H0, the second type is this thing L, and the output is the same L. So this is going to be a concat with H0, L, and L as the output with curly braces. So automatically the compiler can generate an instance of concat with H0 to L is equal to L. So this is how I want to read that. If the compiler needs that. So if the compiler needs such a thing, it can automatically generate that. Now the inductive step is a little bit harder to conceive and to read. So I'm going to define another given. I'm going to call this inductive. And this takes a bunch of arguments. First of all, we will need a natural number n. So I'm going to have an n, which is a type, of course, which is derived from natural. I'm going to have an HA, which is an H list. We have an HB, which is an H list. And an output O, which is an H list as well. So this equivalence is true for any type HA, HB, O, which are H lists, and the type N, which is a natural. So this will make the compiler use, so I'm going to have a using clause. So if I can automatically prove or gain access to somehow for a relationship that says HA plus HB is equal to O, so basically what I'm saying is concat with HA, HB, and O. So if I have access to that, then the compiler can automatically create a concat with N prepended to HA, HB, and N prepended to output with curly braces. So if the compiler can prove the concat between HA and HB is equal to O, then the compiler can also prove that N prepended to HA concatenated with HB is N prepended to the output. All right. So this is the concatenation operation. Let me test that out real quick. So I'm going to define a value, let's call this concat, and I'm going to define that as a concat of, let's say, 0 prepended to 1 prepended to H0. Now this is possible, obviously, because the type : is infix. You can also mark that as infix in Scala 3. It's not mandatory, but it might become in a future version. All right. Anyway, so I'm going to create a concat instance. Now I'm going to make the compiler figure out a concat instance for me. And I'm going to say that concat between 0, 1, and 0, and let's say 2, 3, 0. So basically the list 0, 1, the list 2, 3, and the output is supposed to be 1 or 0, 1, 2, 3, H0. And I will need the compiler to automatically create one for me. So I'm going to have an apply method. So apply that takes, let's say, HA, which is an H list, HB, which is an H list, and output, which is an H list. And I'm going to make the compiler use whatever given instance it can find or it can create. Let's call this concat of HA, HB, and L. I'm going to give this a name. Let's call this concat. Of course, this is going to be with the type not L but O. That's how I named it here. And this is going to be of type concat of HA, HB, and O. And I'm going to basically surface that concat instance. So this is pretty much a summon method. Only that it takes the appropriate type arguments, not just one type argument. All right. So we are going to surface out whatever concat instance the compiler can find or it can generate. So I'm going to say concat.apply. And if the code compiles, then I've already proven that the list 01 concatenated with the list 23 is equal to the list 0123. Right? So if this code compiles, that the compiler can prove the concat relationship between these three types. I can also say equals concat with these types, and this is equivalent to saying concat.apply with the appropriate types, and this is the same thing. So if I recompile this code, you will see that the code compiles just fine. All right, now if I define a value, let's call this invalid concat, and let's say that I mess up some types. For example, I'm going to copy the concat between 01 and 23, and let's say that the concat is supposed to be 0321 h0. And in this case, the code won't compile because the compiler cannot find the appropriate given value of this type. Therefore, it cannot prove the relationship 01 plus 23 is equal to 0321, and therefore, the relationship to say 01 plus the list 23 is equal to 0321 is false because it cannot be proven by the compiler, right? So I'm going to comment that out, and only the correct concatenations will be able to be proven by the compiler due to the fact that we created the appropriate given generators here. So this is the concat operation that is needed for us in Quicksort. Right, that was operation number 1. Operation number 2 is the partitioning. And this is going to be the more complex of the two because we have cases here if the head of a list is bigger or smaller than the pivot that we've chosen. All right, so partitioning means that we're going to split a list into two parts. So the axioms of partitioning are going to be as follows. If I have the empty list, then that's going to be split into the empty list and the empty list. I'm going to denote those as tuples. So this is the empty list, and this is partitioned into the empty list on the left and the empty list on the right. This is pretty basic. Now, if I have a list that contains just one number, I'm going to call this n. I'm actually going to denote that as such. And I'm going to split that by containing the n on the left partition and the empty list on the right partition. So if you want to split a list of just one element into two lists, I'm going to keep the list on the left containing that number and the list to the right to be empty. Now the inductive step is much more complicated. It has some branches, and I'm going to try to explain it as clear as I can, although there are a lot of shorthands here and a lot of type aliases and names. So assume we have a non-empty list with at least one element. Let's call this P prepended to a tail. So this is going to be a head and a tail. This is going to be a list. So if the compiler can prove that this list is partitionable into a P prepended to a left list and a right list, where L and R are inferred by the compiler, then for every type n, which is a natural, we have a branch here. If n is less than p, that is, if this number is less than the pivot, is supposed to stay on the left side. So if n is less than p, then the compiler will automatically create a type relationship which says pnt. So now we have the natural number in between the pivot and the tail. Will partition into pnl. So we have the natural number here on the left side of the partitioning because the n is less than, I'm actually going to say less than or equal to p. And the same right-hand side. So the number n is going to stay on the left side of the partitioning because it's less than or equal to the pivot p. If n is strictly bigger than p, then the list pn T is going to section in or partition into PL and N to the right. So now the number N is going to stay on the right side of the partitioning because it's bigger than my pivot P. Now, this is a lot to take in. So if you want to pause the video, you can. There are a lot of letters and a lot of relationships here. So you might want to revisit the explanation a minute ago. Okay, now I'm going to embody these into given generators for a special trait that I'm going to call partition. So I'm going to define a trait called partition, which takes an initial list, so HL, which is an HList, a left, which is HList, and a right, which is HList. So if the compiler can generate an instance of partition HLLR, then we can say in logical terms, for our purposes, that the original list HL was partitioned successfully into L and R. Cool. So I'm going to define the companion object for partition, and I'm going to write some given generators for these axioms. The first two are comparatively easy, so I'm going to have a given instance. I'm going to call this basic empty, and this is a partition of hnil, which transforms into hnil and hnil. So this is partitioned into two empty lists. So I'm going to say with curly braces. I'm going to define another given instance which says for every natural number, a list containing just that number will partition into the list containing that number and the empty list. So I'm going to call this basic1. And this takes a type argument n, which is a natural. And this will generate a partition of, and the original list is going to be n concatenated to hnil. And this will partition into the same list, n concatenated to hnil, and hnil on the right. So these are my basic axioms. All right, now the complex part. I'm going to define a given instance. I'm going to call this inductive. And this will take a bunch of type arguments. So we have P and L are naturals, and then TLR are lists. So I'm going to have a P as a natural, N as a natural. We have T, the original tail, which is an H list. We have an L, which is an H list, and right, which is an H list. So we have a bunch of type arguments here, and I'm going to say, I'm going to have a using clause, and I'm going to need an instance of partition which denotes this condition. So we said that P prepended to T is partitioned into P prepended to L and R. This is the same as saying partition with the original list PT, the left-hand side of the partitioning PL, and the right-hand side is R. Now, for the first given generator, I also need to include the first condition here, which is to say n is less than p. So I'm going to have n less than or equal to p, which is the same as saying there must be an instance of less than or equal between n and p. I'm actually going to write it like that. So if I have a partition that looks like this, and a less than or equal to relationship between n and p, then this is going to make the compiler capable of generating a new partition instance where I'm going to embody this relationship. So the original list is going to be p, n, t, and this is going to partition into, as we have here, p, n, l, and r. So we have p, n, l, and r. And of course with the appropriate with curly braces. Now, I understand this is a lot to take in, this is pretty hard to read, but I'm going to give an example shortly and demonstrate how this works. And for the other branch, I'm going to create an equivalent given generator, so I'm going to copy this. So I'm going to say given, I'm going to call this inductive2, and this is going to rely on a different kind of partitioning. So inductive2 will say p and TLR, so we have the same type arguments, it doesn't really matter. And we are using a partitioning PT to PL and R, so we have the original condition here embodied in the using clause for this instance. Now the second type relationship is to say n bigger than p, which is the same as saying we must have a less than relationship between p and n. And now if we have this less than relationship, we can partition p and t into, and I'm going to use these two now. So I'm going to have PL and NR, which is to say that P stays on the left and N stays on the right because it's bigger than the pivot. So I'm going to copy this and I'm going to paste it here. So now we have all the axioms for the partitioning operation. This is the hardest that we've done so far. I'm going to give an example. So I'm going to define, before I give an example, I'm going to create an apply method that surfaces out whatever given instance the compiler might find. So I'm going to have a def apply, which takes some arguments, hl, which is an hlist, l, which is an hlist, and r, which is an hlist, and is going to have a using clause. So I'm going to have using partition, which is partition with hl, l, and r. And this is going to return a partition with hl, l, and r. And this is going to be partition. All right, so this is going to be whatever given value the compiler may find. Now, let's work out an example. I'm going to define a partition, and I'm going to invoke the partition apply method on the following list. I'm going to run a very similar example, 2314, or 231 to be a little simpler. So I'm going to have, let's say 2, 3, 1. Let's also add 4 here with hnil. And this is expected to partition into the list _2 _1 in hnil. So everything on the left here on the elements that are smaller than or equal to the pivot. And the right hand side is going to say _3 _4 in hnil. So notice that the code compiles, namely, it proved that the original list 2314 was partitioned successfully into 21 and 34. How does that work? So we need a partition of these types. So I'm going to have the apply requires a partition of these types. Well, how can we obtain a partition of these types? Well, we can run inductive2 in order to create the appropriate partition. So we can run inductive2, and this requires a partition of, and I'm going to ignore the element number 3 here because this is next to the pivot. So inductive2 requires a partition of 214 into 21 hnil and number 4 with hnil. That is because in inductive2 we're comparing the pivot to the right next number. So _2 is compared to _3 and will require a partition of this list into 21 and 4 nil plus a 2 less than 3. So we also need this type relationship which we proved in the previous video. So I'm just going to require this kind of partition, and we are going to assume that 2 is less than 3 as proven in the earlier video. Now, in this case, we have a number 1 which is less than the pivot, so we can apply the inductive step. So not inductive 2, but inductive. And this requires a partition of, and this time we have 2, 4 hnil into 2, and the list just comprised of the element 4. Right, so right now we're comparing _2 to _1, and so we need to partition whatever is left without the element 1. So we have the list 2, 4 partitioned into 2 and 4 on the right because it's bigger. And again, we are going to use inductive 2, which requires a partition. And I'm actually going to copy these types. So I'm going to have a partition of _2 with nil, _2 with nil, and the empty list. So we are ignoring the element number 4. And this is true by virtue of this basic1 given generator. So basic1 generates a partition of the list containing just the element 2, the list containing just the element 2, and the empty list by virtue of this basic generator. And working backwards, the compiler can then create all the intermediate given instances to create the appropriate partition that we requested from the apply method. Now this is a lot to take in, so I recommend that you pause the video and work these step by step. So at this point, the partitioning phase is done. This was the most complicated phase of our quicksort. And in operation number 3, so we have op 3 here, we have quicksort. And I'm going to define a trait I'm going to call qsort, which takes an original list L, or HL, let's call this L, which is an H list, and a type R, or output, which is an H list as well. Now, the axioms of quicksort are as follows. Sorting the empty list is the empty list. This is plain and simple, really, really easy. Now, the inductive step is going to perform all the intermediate operations of quicksort. So for a list, let's call this n prepended to a tail for any natural number n. If we have, and I'm going to add some notes here, if we have a partition, so we have a partition which takes nt as the original list, and we partition that into n to a left, so the pivot is going to stay on the left-hand side of the partitioning, and a right list, for example. If we can sort, so if we can have a qsort of this L, the left-hand side of the sorting, into a sorted list, let's call this SL. If we can also have a qsort of R to some other sorted right, and if we can also concatenate the sorted left, the pivot which we left behind, and the sorted right into the output, so if we can say concat with, let's say, SL and n prepended to the sorted right, so this is to say that we concatenated SL, n, and S right into an output list O, then we can have qsort of n prepended to t, the original list that we want to sort, and our output type O. Now, this is a lot to take in. These are all the conditions for a quicksort to happen, so if the compiler can automatically generate all the appropriate given instances for all the intermediate steps, then it can also generate a qsort for what we want. So, that is to say that if I create an object called qsort, I'm going to define the empty axiom as a given generator. So I'm going to have a given, let's call this basic. And this is going to be a qsort of h-nil and h-nil. This is super easy with curly braces. This is our basic instance. Now, I'm going to have an inductive step. Let's call this inductive. And we're going to take a lot of type arguments here. So we're going to have a number n, which is a natural. So n, which is a natural. We're going to have the tail, which is a list. So tail, which is an h list. We're going to have a list L and a list R. So I'm going to have L, which is an h list, R, which is an h list. And then we're going to have the sorted types SL and SR. So SL, which is an h list, SR, which is an h list. And finally, the output type O, which is also an h list. And then I'm going to have a using clause that will require all the intermediate given instances. So I'm going to say using partitioning with the NT, NL, and R. So I'm going to actually copy all these types because I've written them one by one. So using partition with NT, NL, and R. If I can also have a qsort of L to a sorted left, then I'm going to also require a qsort of the right side into a sorted right. Then I'm also going to require a concatenation between the sorted left and the sorted right into the output type. Then this is going to create a qsort of NT with the output list O with curly braces. So we have all the pieces in place, and I'm going to also define an apply method. So apply with L, which is an H list, and output O, which is an H list, and I'm going to have a using clause, let's call this sort, which is of type qsort with L and O. And this is going to return a qsort of L and O, and this is going to surface out whatever sort instance the compiler can fetch or create. So now we have the qsort in place. Let's test it out. So I'm going to have, let's call this sort test, and I'm going to use qsort with, let's say, 3, 2, 1, 4, h-nil. So I'm going to have to finish with h-nil. And I must say that the sorted instance of this list is going to be 1, 2, 3, and 4, and then h-nil. If the code compiles, then the sorted was correct. And it does. So the code compiles, and therefore the sorted version of 3214 is 1, 2, 3, 4 as expected. Let me define some other sorting tests. So I'm going to have, let's call this sort test number 2. Let's say I have an already sorted list. So I'm going to have this thing here. So we have 1, 2, 3, 4, which also works correctly. Let me define another one. I'm going to write the numbers backwards. So I'm going to have, say, 4, 3, 2, and then 1. Still, the sorted list is going to be 1, 2, 3, 4. Let's rename the variable sorted test number 3. And let's also have another sort test. Let's call this sort test number 4. And I'm going to have some elements of the same type. So I'm going to have underscore 4, underscore 4, underscore 4, and underscore 4. And this is the same sorted list. So I'm going to copy that and I'm going to paste it in the result. And if the code compiles, then the sorting is correct. All right. So we've proven the sorted relationship between 3214 and 1234. This is absolutely amazing, and that is because the compiler can automatically generate the appropriate given values. Now, that's not all. We have defined a quicksort algorithm here designed with given instances, but this is us proving the sorted relationship between lists. I would like the compiler to figure out what the sorted version of a list is, not have me specify what the sorted list should be and have the compiler validate that. And to that end, I'm going to modify my qsort thing. I'm going to call this sort actually. So I'm going to call this sort and sort. And I'm going to intentionally make this qsort type red. You're going to see why in a second. And I'm going to take the generic type parameter here, and I'm going to add it as an abstract type member to this trait. So I'm going to have type O, which is an H list. Now, inside the object sort, I'm actually going to write a type alias. So I'm going to have a type. I'm going to call this qsort, of course, with L, an H list, as an O to H list. And I'm actually going to call this O result so that the O and the result do not collide. And this is the same as saying sort with the type L, where the type result is O. So I moved one generic type argument into an abstract type member, and I've created a type alias, which is to say a sort L where the abstract type member is the generic type argument of this abstract type alias. Now, why have I done that? Well, I've done that so that the compiler can automatically infer what the output type O should be and have it store that result type into my abstract type result so that I can print it out to the console. So I'm going to have a given basic, which is qsort h-nil and h-nil, and I'm going to have a new sort of h-nil with, or rather where the type result is h-nil. So I'm going to have some modifications to make. And at the end here is going to be a qsort of n, t, and o, which is to say that this is going to be a new sort with the original type nt. And rather than using a generic type argument, I'm going to store that type result as o. So I've done a bit of refactoring here, and the apply method needs to also be refactored, so I'm going to cut the type argument here. I'm going to rely on using a sort instance which is of type sort L, sort with L, And the trick here is to return a qsort type alias with L and sort.result, because we can use the generic type argument from the abstract type member of the method parameter. So we can also do that. And I'm going to return that same sort instance. Now, I'm going to have to figure out how to surface that type argument. So I'm going to remove the sort here, and I'm going to remove all the types. So I'm going to have sort3214h0, and the code still compiles, but I need to surface out whatever type member that sort instance may have. And that's going to be a difficult job because the generic type arguments as well as type members are erased and they're not available to the runtime. And to that end, I added a small library, which is here in my build.sbt. This is a very, very tiny library from Rob Norris. It's called typename, and this allows surfacing a two-string representation of an abstract type to the runtime by using macros. So I'm going to import that particular library, and I'm going to have a small method. I'm going to call this print type that takes a type argument A and a value of type A, and I'm going to make a using clause. I'm going to have a type name as type name of type A. Now, type name is a special type from that mini library. That library is so tiny it barely has 20 lines of code, but it's super powerful, and this returns a string. So I'm going to return type name.value. I'm going to explain in a future video how that thing works. It's pretty magical, and it relies on macros to bring the string representation of a generic type to the runtime. So I'm going to return type name.value, which is a string representation of this type name, which is automatically generated for all the types for which I'm requesting that particular type name. All right, cool. So I have a magical method which is supposed to print the generic type string representation to the runtime. Now, what I'm going to do in main is to say, I'm going to type in a main method, and I'm going to print line that little print type method applied to my little sort test, for example. Now, we haven't really tested anything. We only relied on the compiler to do that. And if I work on the type inference on the compiler, we'll see a sort.result here, so not really that useful for our last test. So we're going to rely on this library to print the appropriate type. So let's run this application and hoping for the best. So now we have quite a large representation of this type, but notice we have the type result here surfaced to the runtime. But I'm going to replace this prefix from all the types, so I'm going to have a replace all thing. So I'm going to replace Rock the JVM blog whatever to the empty string. And at this point, we should be able to replace everything with empty and shorten the type a little bit. So let's run the application again, and we have our type result. Now, I'm going to take this out. So notice that the type result is a supertype of the actual type, which was inferred by the compiler, and a subtype of whatever other type was inferred by the compiler. Now I'm going to take this, the center piece of the type signature, because this is what the compiler actually inferred. And let's see what we have here. So we have the concatenation between, or the non-empty list, starting with successor of 0, which is to say _1, then successor of 1, which is to say _2, and the successor of 2, which is 3, and then successor of 3, which is _4, and then a nil. So the compiler automatically inferred that the type result of this little sort test is supposed to be 1, 2, 3, 4, h nil. So the compiler automatically calculated the appropriate result type for our little sort without us needing to specify it manually. So the compiler did this whole bunch of work for us at compile time. Now, folks, if this doesn't show you how powerful the Scala language and compiler is, I'm really not sure what will. This will be probably the most complicated quicksort you've ever written, but this will probably impress your interviewer if they ask you how you can sort lists. You can throw this kind of solution in their face and blow their minds away and triple your salary. Guys, I hope you liked this video. If you did, go ahead and click the like button for me and subscribe to the channel for more videos like this. Probably not as complicated as this though. And follow me on Twitter and LinkedIn as I post fresh updates on upcoming material, and follow my blog and my website here at rockthejvm.com as I have hundreds of hours of content on Scala and functional programming and cats and Akka and Spark and many other goodies in the Scala ecosystem. Until next time, I'm Daniel signing off.